Hello and welcome to AUTOiNFORM online magazine. In this diagnostic workshop feature, I'd like to talk about air mass meters, and in particular, what options we have for both evaluating and testing them. First of all, what exactly does an air mass meter perform in its duty within the engine management system? It's an input load device. It's one of the most critical inputs. Essentially, the engine management computer looks at request. Request is the driver requirement from the vehicle. It then has to compare the request with specified values. Specified values, in effect, are the parameters built within the software in the ECU. And in order to compare those specified values, it has to look then at actual input values. So one of the prime load input value components is the air mass meter. The other obvious one, of course, is the APP, accelerator pedal position or throttle position indicator. Air mass meters now come in basically in two variants, analog or digital. The trend now, of course, is to go entirely to digital air mass meters, and indeed the vehicle we're using today for this presentation is a digital air mass meter, because I'd also like to demonstrate how to test digital air mass meters, which differ slightly in the test process from analog, although some of the data measured is actually the same. It's measuring the mass of air, which is a calculation from the amount of air ingested across the sensor. Some of these sensors have what's known as a diffuser. The diffuser is quite important. If the turbulence of the air were to become, shall we say, quite volatile, then the accuracy of the air mass meter is affected. In some cases, when intake systems are modified with sports induction systems, it often does disrupt that turbulence. So the actual diffuser is there in effect to create a combing or smoothing effect of the air intake, so that the actual sensor, which is actually, this is what they call a bypass type air mass meter, whereby it measures a percentage of the air being drawn in, not the entire volume. It's important that the flow across that sensing element is both even and smooth. So that's essentially what the air mass meter does. What I'd like to discuss are, well, what are some of the options that can go wrong? Because quite often, when technicians are faced with a DTC, which relates to an air mass meter fault, often they immediately go towards the air mass meter. We have to accept that it's monitoring and measuring air intake. So we have to think what sort of things will affect the actual air intake. Obvious things: blocked air cleaner, a disruption in the connections with the hoses between the air intake system and the engine. Now this can include induction hoses. In many cases, once the air has passed through the air mass meter into the turbo, many vehicles now of course are supported with a turbo forced air induction system, then that pressurised air has more opportunity of leaking through hoses which have holes in them, not seating properly, where the clips aren't connected properly into the intercooler, and indeed in some cases the actual intercooler itself, which in effect is a radiator, it's a heat exchanger, actually becomes corroded or has been punctured from debris from the road, and any loss of air after measurement will change the relative value of the load measurement. So in effect what will happen is the air mass meter will measure a value of air mass. The calculation will be made to add the correct amount of fuel against that calculation and others, of course. The air is then pressurised with a turbo and then potentially lost through an induction leak. So in effect what can happen is you end up with an engine that's overfueling. So you may end up with the rather ridiculous situation of an air mass meter value which is correct, but an engine load value or lambda value which is showing lean of normal. Effectively what we're doing is we're drawing air into the engine illegally through an induction leak. It could also be affected by an exhaust leak as well. So there's many options why an air mass meter value could become incorrect. Another very obvious one, of course, is EGR. Where EGR systems are fitted, this particular vehicle does not have EGR. Where EGR is fitted, EGR is used to reduce the temperature in the combustion process by adding exhaust gas back into the intake. That in effect is a passage between the exhaust system and the intake system. If there was a leak between those two systems when one should not be present, in other words, there are many conditions when the EGR system is closed. If that EGR system were to become faulty, then that loss of air between that system will affect two things. It will affect the flow across the air mass meter, and it will also create the wrong calculation from the air mass meter. And it's the EGR that takes its control, one of its control parameters, from the air mass meter value. So we have a situation here where potentially an air mass meter DTC could be caused by a faulty EGR, and a faulty EGR DTC could be caused by air mass meter, and it could all be caused by effectively an air induction leak. So I'd like you to perhaps consider all of those options when you look at a DTC for an air mass meter. The most obvious, of course, and the most common, is that the actual parameters specification of the air mass meter is actually faulty. In other words, the system, the integrity of the system physically is good, where the air mass meter value has changed. In most cases it reduces. I've had the odd case where it's increased. It's quite unusual, but it does happen. And we have to then think about, why does that happen? And the biggest single cause is emissions, breathing, fumes, deposits of oil, which are often recirculated as part of the breathing system of the engine, often become contaminated on the air mass meter. And this can happen when you actually turn the key off. Once you've turned the key off, the oil in the sump's quite hot. It causes vapour to rise. Within that vapour are particles of oil, and that can find its way back into the induction system. You may often find on petrol engines, if you look behind the actual throttle butterfly, it's quite dirty, whereas the leading edge, the front edge, is actually quite clean, and that's because it's the fumes from the engine that are attempting to get back into the induction system. So contamination from a petrol system is not as severe as diesel, because it at least has the butterfly, the throttle butterfly, to prevent some of the contamination. But they still do become contaminated. They can also become contaminated by debris from the atmosphere, from the air, through poor servicing, bad air cleaner performance, dusty environment. So a lot of it is to do with servicing environment, operating conditions. So there are many reasons why these actually fail. So try and take those into account before actually blaming the air mass meter, and please try to remember that any sensor, and this is a sensor, requires power and ground to be correct before the output value will be correct. So the golden rule always is output, power, ground. Never reject an output value without first checking power and ground. And in some cases these may also have a heated element within them, and of course that heating element has to work also. It's quite vital in the functionality of an air mass meter. Some of these have ambient air sensors built in them, some do not. So there's a number of critical functions that this component has to go through. What we've done just prior to setting up for the filming is I'd like to take a look at serial diagnostic opportunity first. I've often argued that serial diagnostics often shows symptoms, not cause. That doesn't mean to say I don't trust the process, I do. However, what I do is question the results of that process. And what we've done with this, I've set up some custom dynamics. In other words, I've chosen or cherry-picked certain key data from which I can evaluate this particular air mass meter. This is a digital air mass meter. Now I'd like to make the point here that there are two views here. To correctly assess the air mass meter fully through the entire engine load, you really need to drive the vehicle on the road, or at least have it on a rolling road. Doesn't exclude the possibility of actually testing air mass meters statically in the workshop, and that's a process that we've done very successfully. The results have been accurate, but I do make the point that if you're going to assess an air mass meter comprehensively, then do it on the road with live dynamics, and take into account other parameters as well. So what I've requested here is engine load is a calculation that the ECU forms from a number of critical inputs from request, components, look at engine temperature, speed, air mass meter, lambda value, throttle, opening position. There's a whole range of inputs from which the computer will calculate load. And what I've actually asked the scan tool to observe is specified load. That's a theoretical load value of the engine from the lookup tables of the actual software program and the actual value. And of course, those should agree at all times. So if specified and actual do not agree, in my opinion, there's an input error. There is something wrong with the system, whether it be a sensor out of value or a physical mechanical fault, but it needs resolving. As to look at engine speed, intake temperature. Intake temperatures affect things like turbo boost. And of course, turbo boost and that performance is also part of the load calculation, which is dramatically affected if the air mass meter signal is wrong. So with turbo engines, not only does fueling become affected, ignition setback will be affected, and also air-fuel ratios, and of course turbo boost control. So we've looked at load. We've also asked for it to look at the actual air mass. This will be a calculated value. This is a digital air mass meter based on frequency. It's very easy to measure frequency. A simple multimeter will do that, and it would be quite possible to use that multimeter frequency measurement to be able to say and compare it with a known good value. Yes, that air mass meter is making the right value at that particular engine load. It's relevant to load, of course, throttle opening position. In our case, we're allowing the PCM to make that calculation for us and convert it into kilograms of air per second. So first of all, what I'd like to do is start the vehicle. Now what will happen is, because this is a static test, not a dynamic test on the road, expect to see a big difference between specified and actual values of engine load, because clearly the throttle's closed, it's not on the road. But I do make the point, driven on the road, specified and actual values of load calculation should match. So if you can kindly start the vehicle, and we'll take a look at some of these values. I'm going to reinstate communication, simply because the engine had been turned off. As you can see, we're looking at live dynamic values. The engine's running, but the vehicle isn't, of course, moving, so I say there will be some differences in value. We're looking at, you can see a big difference between specified and actual engine load, simply because the vehicle is static. What I'd like to draw your attention to for this particular test is the value of air mass in grams per second, because this takes into account, in effect, what's being measured across the air mass meter. Now, tested in the way we are now testing it, there is a number of possibilities. Because the turbo's not on boost, there may or may not be a leak in the induction system, and there may or not be a range error present at this point in its load characteristics. So this is purely a static test only. We could rev the engine up, and of course that figure will increase. There's little value in that at the moment, for the same reason, that we're not simulating full load accurately as though the engine were being driven on the road. So I think I've stressed the point enough. But really, intuitive testing on load, drive the vehicle and look at the specified actual values of load and actual air mass meter value. Out of interest, if you calculate the engine brake horsepower, this is a standard 265 horsepower engine, and multiply it by 0.8, the result of that calculation should equal the maximum air mass meter value in grams per second on full load. So if you're never sure what the air mass meter full load value should be, you can always work it back from the brake horsepower, and it does tend to be quite accurate, with one exception. If the vehicle has performance software fitted, and this does, it will then increase the flow of the air mass meter slightly, and also the brake horsepower, and therefore the two should still match, but you will end up with a figure higher than the standard specification, because obviously you've increased the brake horsepower. So The point I'm making here is that we can use serial communication to accurately assess the value of the air mass meter dynamically and or statically in the workshop. That said, what I'd now like to show you is how do we then actually test the air mass meter by other means. When air mass meters went digital, it presented a challenge, and the challenge was that previously we would compare the analog value, which is a voltage, against lambda, and the throttle position indicator, or APP. And that gave us a very nice linear graph which was very easy to interpret. When digital air mass meters came out, that presented a problem that the frequency of the air mass meter, which will vary in our case from around 800 Hertz, Hertz is 1 event per second, to about 9,600 on full load, that frequency could not be displayed on an oscilloscope with things like lambda and APP. So it took us a while to be able to resolve this issue. It's been resolved in two ways. It's been resolved with some very nice software in the Picoscope, which I'm going to demonstrate, and it's also been resolved with the introduction of a current clamp. We actually introduced the current clamp before the software was introduced, so we now have two options of converting a digital air mass meter into an understandable and intuitive test. And it's very interesting that the results of both current and digital conversion are quite unique in their characteristics. So I think you'll see that this is really quite an interesting way of testing air mass meters. We've also used current on analog air mass meters with the same accuracy and results. So it's an interesting avenue we're starting to develop, and we're starting to gain a lot of confidence in the current that we measure through the air mass meter, rather than looking at voltage and or a calculated value. It helps us understand that the air mass meter is correctly interpreting the air mass by the change in current flow across the sensing element. But all that said, what we'll do now is switch off for a moment, set the next test up, and then join us shortly, and then we'll show you the two tests. One is conversion of frequency to an analog value, and then also frequency or load in current across the air mass meter. So, see you in the near future. Welcome back. During the short break, what I've done is set up the oscilloscope with three options of looking at a digital air mass meter. One is to actually measure the frequency, and I have made the point you can use a multimeter for this. Secondly, to look at the conversion of that frequency to an analog display, and third, to look at current flow. So what I'd like to do first of all is show you the connectivity and then discuss the setup options actually on the screen. I'll begin with the current measurement. One of the challenges of measuring current in very low values was to get the signal to noise ratio resolved. In other words, background noise. Often when you reduce the sensitivity of any measurement, voltage or current, then any background noise effectively obliterates the signal. We did manage to find a current clamp that measured from 0 to 450 milliamps, 0 to half an amp, with a great deal of clarity in its resolution. And that was our initial conquest of converting digital to analog, but looking at current, of course, not voltage. The device connects by means of induction. I think it's actually a whole device, and the sensitivity, I say, is such that it can measure accurately very low amounts of current flow through a circuit. With the air mass meter, we attach this device to the power cable to the air mass meter. Remember, output, power, ground, all devices will have all three. The power lead to the air mass meter with the arrow towards the device. The device is the air mass meter. Ensuring the doors are fully shut and not obstructed in any way at all. the actual output signal frequency has been connected with two channels, channel A blue, channel B in red, on the same pin, because I want to show one as a frequency and show one as a conversion, which I'm going to show you the actual setup for that. And that connection is in the third pin of the air mass meter, closest to the engine intake. So in other words, the pin nearest the engine intake is the output signal. That said, the actual setup now of the oscilloscope. The actual frequency signal on channel 1, blue, is over a 5 volt range. Now the reason it's shown as an envelope is that it's a high frequency, somewhere around 2000 Hertz at present, the engine's idling, and because of the time base we've selected, the signal becomes compressed. So if you want to look at that in detail, of course we need to divide into the voltage, into the time base. So if I select a more reasonable time base, say 1 millisecond, you can see very clearly it is a digital output and has a frequency. We can request measurement of that frequency with measurements, add measurement on channel A, which I'm going to leave as a frequency, and request frequency as the option, and apply it. And we now have a pop-up box, and the average is 2,250 odd kilohertz, 2,200 hertz approximately, which is about the expected value given the current load condition of this engine, or current air intake value of this engine. Now the problem is, if I now want to look at this air mass meter historically over a trend over several seconds, and I normally use 20-50 seconds of real time, I can't view a frequency, nor can the oscilloscope calculate a frequency for me, nor can it show trend. So I need to go back to my original setting and now apply a 50-second time base. That's nearly 1 minute, of course. It's a 10 grid screen, so 5 seconds per division will give me 50 seconds. For this particular test, I can probably get away with 20 seconds, so I'm going to reduce it to 2 seconds per division. That gives me 20 seconds across the grid. So in other words, the sweep time now is 20 seconds. Now you can see we've gone back to this envelope, this compressed image, which has no diagnostic value at all. However, we are measuring current. Now the conversion factor for that tool is every volt is 100 milliamps. So we're looking at somewhere around 1 volt. In fact, we can measure it quite accurately. If I place the cursor on the green line, which is current, channel C, 1.029 volts. That's 100 milliamps of current flow. Now what we found very, very interesting is that irrespective of engine size, we're getting very, very similar current flows across air mass meters. Even on full load. Now what I'm suggesting there is, irrespective of the volume of an engine or the performance of an engine, we are getting some very similar, very, very similar figures. And 1 volt at idle, 100 milliamps, is a very consistent value. So we're having some confidence in interpreting this as a means of testing air mass across an entire range of engine systems. So what we're looking at there in green is current. At the moment, the red channel, channel B, is still measuring the frequency over a different voltage range, which is why the image size is smaller than channel A. But I want to convert the channel 2 into an analog interpretation of frequency. To do that, I go on to the coupling request. It's a DC coupling at the moment. Open the box, select frequency. I now need to look at range, because we're already at 2200. We have a 0 to 2000 range, so we're going to get no display because we're already above that reference. The next range is 0 to 20,000, that's ideal, so I'm going to select the higher range. I've shifted the baseline so that 0, this is now frequency, kilohertz, 0 to 20,000. We now have a reading, and you can see 2000, we're just slightly over the 2000 kilohertz. So we now have a representation both of current and of output value converted from that signal. So we've converted that into that, and we're measuring current. Now we can conduct an historic test over a period of time, and I could also add to this measurement lambda. I don't intend to do that for this presentation. We've done that previously in the magazine. This is purely on air mass meter interpretation, digital air mass meter interpretation, to give you an idea how accurate both methods of measurement are. Well, three methods: pure frequency, current conversion, and digital to analog conversion. So what I'd like to do now, I'm going to walk around, open the throttle pedal, collect the data, and then we'll come back and we'll switch the engine off and actually analyse the results. I'm simply going to wait just until the image starts to write from the left of the screen. I want to get the whole of the display in the centre of the screen. And of course you can conduct this test over a wide operating range, so I'm letting the engine natural idle. We'll open the throttle now. Let it recover to natural idle and switch off. I'm going to retrace the capture by one screen. Now, I think it's very obvious from what you see here that current in green and the conversion from frequency to analog using the Pico software is remarkably similar. So if we now slide up the two, apart from there being a range differential, and I can't range it anymore, this is just a range condition now, whereby the amplitude of the signals is varying only because of the ranges available to me. But I think you will appreciate the incredible accuracy of both of those methods of assessment. I did make the point that to test an air mass meter thoroughly through the entire operating range, you should load the car, either on the road or on a dynamometer. However, even under workshop conditions, a static car, we have found these tests incredibly accurate. And of course, you're comparing known data. We're comparing the exact condition of this system with another one. And of course, we store this data in our archives so that we know exactly how much current flow passes through this device and exactly what frequencies they are. Also, I mentioned that the maximum output in terms of current also has been remarkably accurate. Most engines produce 170 milliamps on full load, peak. This has got some software in it. So what I'm going to do is just measure the peak output, current in green, and it should be just over 2 volts, 200 milliamps, yes, 200 milliamps. So I've clipped it, in fact it's just gone off the screen. and it is 2.011 volts, 200 milliamps, because this does have level 2 software fitted to it. So the increase in output is purely a function of that software change. But we are finding some remarkably accurate, consistent and reliable results, both with the conversion through the software and through current measurement. And I would thoroughly recommend it as two options which are very well worth introducing to your diagnostic process. The current clamp also serves very usefully for other very high speed current devices, such as anything that's now motor driven with PWM signal, where current and frequency changes very, very quickly, where duty and frequency changes, therefore current, very, very quickly. Turbo control, motorized throttle body, EGR control, variable intake flaps, it just goes on and on. Everything now is motor driven. So I think that more or less concludes, I hope, some thoughtful suggestions before you blame the air mass meter. Look at other potential conditions. We test integrity of air intake systems using smoke, and we're going to demonstrate that also a little later on. And bear in mind that these, if they do become damaged or affected, try and think about curing the causes and not dealing with the symptoms. And quite often there are some very, very progressive treatments now for engines, some flushes and intake system treatments, which can help recover the condition, especially with diesel. Diesel intake systems really do get very, very badly contaminated, and we're now looking quite thoroughly into processes to recover the condition of the engine without major mechanical dismantling and work which involves replacement of very expensive parts. EGR valves, air intake systems, quite expensive replacement parts. So we're now looking to other methods of recovering those. So don't blame the failure of an air mass meter purely on its own devices. These, left alone in the right environment, often are very, very reliable. Well, that concludes the presentation. I hope you found the advice interesting and useful, and I look forward to seeing you in the next edition. Thank you.